Welcome to module 37. Last time we introduced the notion of local connectivity and local path connectivity and proved a few results there. So today we will examine a number of illustrative examples. Either they are counter examples or they are positive examples and so on. The first example is what you have already met. Okay, it's very easy to state, which will be locally connected but not locally path connected. This is very easy to state, namely the cofinite topology on, say, take set of integers or natural numbers and any countably infinite set. Okay, countability is important, infinite also important. Okay, if you don't take infinite, finite set, the cofinite topology will be discrete topology. Discrete topology with more than one point is neither connected nor path connected, but surprisingly, because points are open, this is both locally path connected as well as path connected, locally path connected. So I am not interested in discrete topology. All right. So the first thing is every non-empty open set will intersect every other non-empty open set in the cofinite topology because the complements are finite, right? So a finite set cannot contain another set which is its complement is finite. That is not possible when the whole thing is infinite. So any two open sets intersect, therefore there is no separation. Okay, that means that the space is connected. Similarly, it is locally connected also because every open set will be also the same property. You can't separate it out. You take any open set, that itself will serve as a connected neighborhood. Inside that, you have to take connect. It's already connected, right? The subspace topology on a open set is again the cofinite topology only, and it is uncountable. It is countable and infinite. Therefore, this space is locally connected and connected. However, we claim that every continuous function omega from closed interval 0, 1 into this space is a constant. Once we prove that, it follows that two distinct points cannot be connected by a path. Okay, so we are going to prove that strongly that the path connected components of this space are singletons. Okay, strongly path disconnected in that sense. Okay, so let us see how we prove this one. Suppose you have a path which is non-constant. That means what? The image should contain at least 2 points. Okay. Every point in X is a closed point. Singleton X is closed. Why? Because the complement is open. That's all. Okay. It would follow that the closed interval 0, 1 is a countable disjoint union of proper closed sets. What are those closed sets? Just take omega inverse of singletons. closed set, singletons are closed. Omega is continuous, omega inverse is closed subset. As X range is over its image of omega, Y must be image of omega contained inside X. Take the disjoint union. These are the fibers after all. So they are disjoint, right? Disjoint union. Each of them is closed. What is Y? Y is omega of 0, 1, the image. The points are varying over Y. Okay, there are at least 2 of them. Okay, 0, 1 has been written as disjoint union of closed sets. Okay. One thing is clear, namely this Y cannot be finite. Why? If this Y is finite, this will give you a partition of 0, 1, but 0, 1 is connected. So there is no partition. Okay, there is no separation. This will give you a separation. So that is not possible. All right. Because once, if there are finitely many, you take one of them, everything is closed. The finite union of other things also closed. So you can write a disjoint union of two non-empty closed subsets. Then that's over. But if it is infinite, then there is no contradiction. Okay. So 0, 1 may be connected, but you can always write it as disjoint union of singleton sets, for example. Singleton sets are closed. So that is not a contradiction. Okay. So what we are going to prove is, somehow I want to get a contradiction to such a description. The first thing is I notice Y has to be infinite. But what I am going to prove is the following. A general statement. No closed interval AB, A less than B, is a countable disjoint union of proper closed sets. Y being a subset of X, X being countable, this Y will be countable. Okay. Therefore, immediately this description is not possible is a conclusion. When I take AB to be the interval 0, 1. So this is a general statement I am going to prove. In this one, I am assuming that countable means finite also, which we have seen that finiteness is not possible. That is easy because all intervals are connected. So the point is now countable is not possible is what we have to see. Okay. So here we will have to use Baer's category theorem in a clever way. So that gives you an opportunity to use Baer's category theorem. So watch out. Suppose you have AB equal to disjoint union of FNs, where each FN is a closed proper subset of AB. Okay. You see, if FNs are empty and one of them is AB, then there is no contradiction. So they must be proper. That is important. Proper means what? Non-empty as well as not the whole space. Take Dn equal to the boundary of Fn. By this I mean the boundary points of Fn inside AB. They are all subspecies of AB now. The usual topology of AB. Take Dn as boundary of Fn and take this D equal to union of all these Dn's. Okay. Note that since AB is connected and each Fn is a closed subset of AB, no Fn is open. If Fn is open, what happens? If one of them Fn is open, what happens? It's also closed, I have assumed. Right? Each of Fn is closed to begin with. So proper non-empty closed and open subset will contradict. So since they are closed, they are not open is a consequence. Okay. So when you take interior is a strictly smaller subset than Fn. When you throw away the interior from Fn, what you get is the boundary. Because Fn's are already closed, I don't have to take the closure. Remember, what is the boundary points? Boundary points are closure minus the interior. So closure is Fn itself, interior is empty. Sorry, interior is not the whole space. So interior may not be empty, but you throw away the interior, Dn's boundary of Fn's are non-empty. Boundaries of Fn's would have been empty if Fn is open also. Therefore, each Dn is non-empty. Boundary of a subset is always a closed subset of the set. The set is closed, so these are all closed subsets of AB. Okay, Dn's are non-empty closed subsets. Okay, it also follows that Dn is infinite, but we are not actually using this fact. Okay, Dn's are infinite means what? Each of them I have proved that they are non-empty, and to begin with I have taken these things are infinite. If this is finite, then we already know that the case is over. Okay, but this fact we are not going to use. Okay, right now our argument will include this also. Anyway, so each Dn is non-empty closed subset, right? But now we have lost because these Dn's don't cover AB. Right? The Fn's are covering AB. Now I have taken smaller subsets. So what do I do with them? Take D, which is equal to union of all Dn's, right? How do you get Dn's? By deleting the interiors of each Fn, right? Therefore, this AB minus interior of all Fn's is precisely equal to D. Okay, therefore, this is a closed subset of AB. Therefore, it's a complete metric space. Now, using Baer's category theorem, we will arrive at a contradiction. How do you use Baer's category theorem? Namely, if we show that each Dn has empty interior inside D, okay, then the proof will be over. This is very important because Dn's are boundary of Fn. I have removed all the interior points there, so you may say it is over. No. These interior points were inside AB. Now I have a different subspace. We have this subspace, namely D. I am applying the Baer's category theorem to this complete metric space D. So I have to show that each Dn has empty interior inside D. Okay, then the Baer's category theorem says that countable union of such things are again no evidence. They can't be the whole of D. Okay, so that is the end of the proof, right? So let us go ahead. How to show that Dn has empty interior? Okay, take any point in Dn, show that no, by the way, what is the topology? Topology is coming from R, right? From AB. Everything is subspace of R, right? So take a open interval around a point, intersect it with D. If it's contained inside Dn, that will be the interior. Okay. Take an interval, intersect it with D, show that that is not contained inside Dn. Then it will follow that interior of Dn is empty. So this should be able to do for every point of Dn. What is Dn? Boundary of Fn. Take a point and take an interval around that one. By the definition of boundary, okay, J must, boundary now I am using Fn. Point of Dn is a point of Fn also, but it's a boundary point of Fn. First, you use that property that Dn is a boundary of Fn. Okay, by the definition of boundary, J must intersect both Fn and complement of Fn, right? So it intersects the complement of Fn, where inside the closed interval AB, okay, hence must contain some point of some other Fm, because the entire AB is written as disjoint union of Fn's. If a subset is not contained inside one particular Fn, it must intersect some other Fm, m not equal to n. Okay, now suppose J does not intersect the Dm, boundary of Fm. Dm is boundary of Fm. Okay, that means that it intersects the interior of Fm. All right, it intersects Fm, it doesn't intersect the boundary. So what is left out? It must be interior of Fm, must be. But then what happens? Interior of Fm, this interior is taken inside the closed interval AB. Remember that. Interior of Fm is an open set. Complement of Fm is also an open set. If you take J intersection this and J intersection that, that will be the whole of J intersection AB. I have not written AB here because I am taking the interval J itself inside the interval AB. Okay, so therefore this will give you a separation of J, and that's a contradiction. Therefore, this J, I said J must intersect Dm, the boundary of M. Okay. So what has happened? I started with an interval around a point in Dn that intersects Dm, m not equal to n. But these are disjoint sets, right? Therefore, this J is not contained inside Dn. So there is a point D, after all of Dm is also contained inside D. So J intersection D, there's a point here which is not inside Dn. This shows that Dn has empty interior inside D. And that proves that no closed interval can be written as a countable union of disjoint, closed subsets, proper closed subsets. In particular, the cofinite topology on a countable set is what happens? Is not path connected. Every path component is a singleton. Let me give you some other examples now. This is called the broom space. Let me show you the picture here and then explain. So I start with a closed interval. So let us call this 0 to 1. Okay. Here I take the line segment between 0, 0 and 1, 0 in the plane. So this is 1 by 2, sorry, this is 1, 0. What 0? No, it's 1, 1. This is 1, 0. So 0, 0, and this is 1, 1. This is 1 by 1, 1 by 2. This is 1, 1 by 3. This is 1, 1 by 4, and so on, dot, 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 dot. So 1, 1 by n approaching 1, 0 here. All those points join to 0, 0. So it looks like a broom. This is the broom space. This is the closed subset of R cross R. It is closed and bounded also. Okay, the whole thing is contained inside the square I cross I. Clearly, it is star-shaped at this point. Right? Take any point, there is a line segment to this point. Therefore, this is path connected. Therefore, this is connected. So why this example is there? For the reason that, take a point here on the x-axis, 0 to 1. Say, let us take this itself. namely 1, 0. If you take any neighborhood of that, take a ball around that and intersect with this one, you will have lots of these line segment disjoint sets. No matter how small this ball you are taking, okay, it is going to be intersection with this space will be disconnected. Infinitely many line segments will be there, along with a small line segment on the x-axis. So at this point, it is not locally connected or locally path connected. The same thing holds for all the points here except the point 0, 0. At 0, 0, it's clear. If you take any neighborhood, then you can take a small ball around that, then it will be star-shaped again. So there is no problem. Okay, so that is the Broom space here. So it is path connected. It is not locally path connected at any point actually on the x-axis except 0, 0. At least 1, 0, it's easy. All right. So let us go to slightly more complicatedness. Namely, what I do, I take a small copy of the Broom space here again. I have not drawn all these lines here. They are there inside. Okay, so this is the Broom space B. So instead of 0 to 1, I have made it 0 to half here. Okay, this is 0, 0. This is half 0. This is 3/4 0, and so on. Take half of each time. Take the side also like this, also make it half. Keep making half like that. So this will go ad infinitum. Infinitely many of these things will be there. Okay. Along with this just point will be there, last one. There is nothing there left out. If you come slightly out of that point, you will have lots of brooms here. Infinitely many brooms. Okay. So this is again, the whole thing is contained inside I cross I. Okay, and it's a closed subspace. Remember, I haven't drawn these. There are from 1 by 1, this is 1, this is 1 by 2, comma 1 by 2. You can join them. You have joined them. All those things are there. So this is iterative Broom space. So here I have defined it. Denote the Broom space defined above by B in the first one. Scale it down by a factor of 1 by 2 power n. And shift it at the point 2 power n minus 1 by 2 power n minus 1 comma 0. So all these points approaching 1 comma 0 to obtain Bn. Let B twiddle be the point 0, 1 comma 0 has to be there. Okay, you take that one, union all the Bn's. Okay, now show that every open connected subset of B twiddle which contains 1 comma 0 contains the entire segment 0, 1 comma 0. Okay, the entire line segment, the x-axis part. However, show that every neighborhood of 1 comma 0 contains a connected neighborhood, and hence B twiddle is weakly locally connected at the point 1 comma 0, but not locally connected at the point 1 comma 0. If you want an open connected set, you will have a problem. If you don't want open connected set, just a connected subset, they are there. This is the whole idea. So let us try to see this one, at least some part. After all, I have left this as an exercise to you, but let me just explain. The first part is to show that every open connected subset B twiddle which contains 1, comma 0, contains the whole line segment. Therefore, it cannot be arbitrarily small. That's all. You can't have a connected open subset which is arbitrarily small. If you show that one. So how do you show that? Go to this picture. I want to take an open connected subset. So what you have to do, take a open ball around this one, which you have taken an open ball around this one, right? And intersect with this space. As soon as you take an open ball around this one, infinitely many of these triangles or these brooms are already contained inside this one. Okay. Nevertheless, what happens, because it is an open thing, okay, suppose you have come up till here, there will be always a line from here to here, half going. So this is precisely what I have to. At some point, okay, suppose this point is there, then a small neighborhood of that point must be there in your open set. Then all line segments will be there. So in order that those line segments are connected, you have to go to the base of this. You have to go to the base of that broom. That means suppose once you have, suppose this one is 2 power n minus 1 minus 1 divided by 2 power n minus 1, somewhere here. This point is there means there is small neighborhood around that one is there. Then there will be a line from here to this point. Therefore, this point is there. Okay, so you just keep this whole line segment will be there because it's connected. There is no other way to connect this point and this point. Now, once this point is there, a small neighborhood around that will be there because I am assuming openness, open connectedness. Then there will be some line here, some point here, and the line all the way up to this one. So this way you will end up here. This entire line segment will have to be there in any connected open subset containing any of these points, in particular 1, 0. Okay, you will have to keep backwards. Forward, you don't have to worry. So if you take a neighborhood here, you don't go forward, but you go all the way here. That is the point. So for a 1, 0, the whole line segment will be there. All right. So connected open set is a problem. On the other hand, take a point here, then 1, 0, take a neighborhood. Now don't go backwards. Look at wherever you have stopped up till here. Okay, that will be a connected neighborhood. That is not an open set. You just take the broom only. Don't take all these points. Up to broom you take. Okay, everything forward. So that will be a connected neighborhood. It's a neighborhood because a smaller open subset will be there. A smaller open subset will be there which is not connected. But this is connected and it is contained in the original neighborhood. Therefore, this is weakly locally connected at this point. Okay, and not locally connected. All right, I come back to the topology sine curve. Now it will be very easy, but we will have to just sum it up. The topology sine curve, we see that it is connected but not path connected, that we have seen. Now take any point P on the y-axis part. Okay, x coordinate 0, y coordinate is some point P, and take epsilon to be less than half, just for being safe. Then the ball B epsilon P intersect with the topology sine curve consists of infinitely many disjoint arcs on the graph. For the same reason that we have discussed for the broom space, what happens is the topology sine curve is not connected at any point, locally connected at any point on the y-axis. Okay, let us have a picture of this one first here. So on the y-axis here, you take any ball around here. Ball should not be such that it contains the line segment here and line segment here. At y equal to 1 and y equal to -1. So I take the ball of say epsilon by 2, so or 1 by 2, less than epsilon 1 by less than 1 by 2. Take a ball here, let us magnify it. Okay, so magnify it and look at it. What you look at it, this may be your point, and that means the epsilon ball. You will let all these curves, okay, part of the curves, what curve? Sin pi by x curve. Going and going like this. I have drawn this one thick line. This is not a thick line, this is just a line. There are infinitely many lines like this, infinitely many arcs like this coming. That's why it looks thick. That's all. If you again magnify this, taking a small ball here, it will have the same picture again. There will be infinitely many components there. So this is locally not even connected. So it is not locally path connected either for every point on the xy axis. So this is similar to the Broom space there, okay? But it has this property also, is what we wanted to tell you that. Thus, let us consolidate what are the things that we have done for topology sine curve. It is neither locally connected nor locally path connected. Just now we saw. The topology sine curve serves as an example, or you can say counterexample, to show that connectedness does not imply path connectedness, local path connectedness, or even local connectedness, because it's a connected space, but it is neither of any of these things. The closure of a path connected set need not be path connected, because the sine part, sine graph, the graph of sine x part is connected part. Its closure is the whole space, and that is not path connected. So finally, NLO of 3.34 is not valid for path connectedness. What was NL 3.4? 3.4 said that if the bottom space is connected, the fibers are connected of a quotient map, then the top space is connected. So if you replace path connected everywhere, if you connectedness is replaced by path connectivity, the theorem as such is false. So that is the meaning of this one. So all these things we have seen. Okay, now I will come to another important part here. Maybe that is the last part for today. How to use connectivity positively to derive some interesting results. Okay, so here is something. Look at the intersection of, union of the two axes, x-axis and y-axis. If you are bothered about be too big and so on, cut it off, mod x less than equal to y, mod y less than equal to 1, mod x less than equal to 1, mod y less than equal to 1. Okay, so this is just x-axis and y-axis, -1 to +1, -1 to +1. You can feel that this space is not homeomorphic to an interval. This is also compact metric space, So whatever topological property that you have seen so far will not be of any use other than connectivity. Both of them are connected also. Both of them are path connected. Okay, so what is that? How to use connectivity to show that it is not homeomorphic to a closed interval, -1 + 1. -1 + 1 I take because just mod. You cannot take any closed interval. They are all homeomorphic to each other, but they are not homeomorphic to this space X. Okay, so how to see that? Suppose you have a homeomorphism from here to here. Now take a point here, take its image. The image is one point. Remove both of them from from their spaces. Namely, from the domain you remove this point, codomain you remove its image. Remove that. Then the homeomorphism, whatever let's call F, restricts to the subspaces. That will be homeomorphism again. A homeomorphism from X to Y restricts to a homeomorphism from A to FA for any subspace FA. Okay, so that's easy to see. That is what I am going to use here. My A will be -1 + 1 -0. Then that A we know is disconnected, has two components. Right? Right? If I go here, will it always have two components? That is the point, right? So what I want to do, immediately I see one nice way of looking at it. Namely, remove 0, 0 from here. The point of intersection of the two lines. Immediately you see that there are 4 path connected components for the complement. So take a homeomorphism this way, other way around. X2 -1 + 1. Remove the origin here. Remove the image of that here. Image of that may be any point, I don't know which point. I am just removing one point from -1 to +1. What do I get? If the point I removed is the end point, then the space is still connected, path connected. If it happens to be somewhere between, namely -1 less than fx less than 1, then it will have 2 components. But here I have 4 components. A homeomorphism has to induce what? Bijectivity of the connected components, bijectivity of path connected components. So what is wrong? Namely, our assumption is wrong that there is a homeomorphism from X to -1 + 1. Okay, so that is the gist of this one. X -0, 0 to -1 + 1 minus f of 0, 0. That will be homeomorphism. This has 4 components. This has at most 2 components. Some cases it may have 1 component. So that is a contradiction. Okay. Now I have listed a number of exercises. One of the exercises here, exercise 3.55 for example, is directly from this one, from the last example that I gave you. What did he say? Take English capital letters, okay, as subspaces of your plane, namely R cross R. M, N, Z. Look at all these. I claim that they are all homeomorphic to each other. In fact, they are all homeomorphic to an interval. Easy to see that, right? You can straighten out these things. That is the meaning of after topology, homeomorphism. But none of them is homeomorphic to the letter O. Can you see that why? If there is a homeomorphism here, you remove a point here from here. Okay, remove a point from here. What happens? That is still connected, right? But here, if the point has to be removed only from the interior, so what you should do, start with homeomorphism here to here, take an interior point here, remove it, there will be 2 components. No matter what point you remove here, it has only 1 component from the circle, from the shape O. The shape O you can think of as a circle, it is homeomorphic circle. Remove 1 point, is still connected. So none of them is homeomorphic to this one. So this is another example I am giving you here. So using this idea, what I am telling you is classify all letters that 26 letters up to homeomorphism. Okay, enjoy this exercise. There are other things which you can have a look at it. Okay. So this exercise, for example, is about matrix spaces, and part of it, most of them are from linear algebra and little bit of analysis. But last one is GLN, SON, etc. Whatever you have met last time, they are all locally path connected spaces. The previous exercise told you that they are connected. Therefore, they will be path connected. So the exercise here is to show that they are locally path connected. The challenge. So all these earlier exercises will help you to solve that. Thank you. So let us close it here.